Thank you very much for invitation to this remote seminar. Yeah, I hope everyone is okay and free of viruses of all kinds. So you can see my screen, right?
Yes.
Okay.
Yes, yeah, I also can see.
So I'll talk about quantum mechanics of large N tensors, but this actually includes also rank 2 and rank 1 tensors, namely matrices and fermionic vectors. And I'll end my talk with some new stuff that we published a couple months ago on these models. Okay, so this is my coronavirus reading list for you. Not very exciting maybe by general standards, but yeah, it's a list of various papers that I wrote on models of this type. Actually, I gave a remote talk to your conference last June. So I decided to pick a different topic this time and emphasize the spectrum of energies of these models and the densities of states. So in particular, I'll end the talk with this new paper with former Princeton undergraduate Gaitan and my current graduate students Polygar and Popov and Kirill Pokrovsky, who's a postdoc at Princeton. Okay. So 3 large N limits. This is always the beginning of such talks. So basically, we all know about the ON vector models back from the 50s and 60s, and they're exactly solvable because you're summing a very simple class of diagrams called the cactus diagrams, which are really trees of bubbles. So here are 3 examples of these cactus diagrams. Then matrix or 12th limit, then we of course get planar diagrams, and this is our dream for solving QCD, but we're not done yet, so it's not always solvable. It's solvable only in special cases. And then the relatively new limit, which I learned about only maybe three and a half years ago, which is tensors of rank 3 and higher. And then there is actually another simple class of diagrams which dominates, called the Malonic Diagrams. And this dates back around 10 years back. And in fact, the term Malonic was coined in this paper by Banzom and collaborators. And here is a plot of Malonic, simple Malonic diagrams in a quartic theory. They're basically obtained by inserting what we usually call a sunset propagator insertion repeatedly. And I'll talk about this. So to introduce the basics of the subject, let me talk about matrix model, but of maybe a slightly unusual kind, where we don't consider Hermitian matrices, but consider general real matrices. In other words, you don't assume any symmetry between the matrices A and B. So these matrices are in the bifundamental representation of ON cross ON, where the first index can be red and the second index green. Then the interaction has to be at least quartic, and the most basic single trace interaction is like this. It's trace phi transpose phi transpose. And propagators are, of course, represented by colored double lines, while the vertex has this nice colorful structure with alternating green and red lines. If you consider just the integral over such matrices, such a matrix, or quantum mechanics of such a matrix, then we get solvable models. And the type of graphs you get are basically planar graphs, where the dual lattice is shown in black, and it really can be thought of as consisting of squares. And each square sits at the center of either a red index loop or a green index loop. So you only glue these squares in a particular way, where red is glued to red and green is glued to green. So it's a particular kind of matrix model which can be solved and has been solved in the past. But now, if we then go to tensors and think of a 3-index tensor with 3 distinguishable indices, then we find something relatively new. Not unless you heard my talks on this already a couple years back, but I'm going to repeat myself. So then, again, the indices are distinguishable, and the propagator of the matrix of this tensor, which has this index structure, may be represented by a triply stranded line with 3 separate colors. And the whole, so this seems like a much more complicated theory than the matrix model. And actually work on this began already in the early 90s, but somehow back then people could not find an intelligible large-n limit for these models. It just seemed too complicated. But then it was discovered that if you include special kinds of interactions, for example, the so-called tetrahedral or tetrahedron interaction, which is shown here, it's really a it can't be drawn on a plane. It's obtained by inserting 2 middle blue lines, which are sort of go under each other and in this way. So you can start with this ON cross ON matrix model vertex and then add these middle lines. Then you can imagine this as just looking from above on a tetrahedron. Then you see that the structure of this vertex, which is shown here, is such that every pair of tensors has only a single contraction. For example, these 2 have only A1 contracted, these 2 have only B1 contracted, and so on. And with this type of interaction, you actually filter out only these Malonic graphs in a particular kind of large-n limit. I won't go over the proof of this. This was actually first pointed out in the 0-dimensional case by Carrozza and Tanasa, who are old experts on these tensor models. And then about a year later was adopted by Tarnopolsky and myself for the fermionic quantum mechanical model, which I'll mention soon. So basically, if you take this particular quartic vertex and just insert it into diagrams, you see that the leading correction to the propagator has at most 3 index loops. You see this 1 blue index loop, 1 green, and 1 red. So this is really of order g squared times n cubed, because each loop brings a factor of n. And requiring that this Malon insertion is of order 1 means that we should be taking the large n limit, keeping lambda, which is gn to the 3 halves fixed. And then all the Malonic graphs are actually obtained by iterating this type of insertion. You can do various estimates by hand. In this particular case, there is a simple proof that why there is nothing that beats this scaling, which can be found, for example, in my paper with Tarnopolsky or the Carrozza-Tanasa paper. So for example, if you look at vacuum graphs, you see that everything scales nicely in this case. For example, this basic vacuum Malon graph scales as g squared n to the 6. So n cubed goes outside, and then there is lambda squared. You expect, because there are n cubed degrees of freedom, you expect all the vacuum graphs to scale as n cubed, and then this one also scales as n cubed, but lambda to the 4th and so on. Okay, and then, for example, all the graphs with odd numbers of vertices can be shown to be suppressed and not Malonic. This is a simple example of such a graph. And then if you want a list of, for example, in a book by Kleinert and Schulte-Frohlinde, there are all vacuum graphs for a quartic theory. And you see that most of them are not Malonic. There are only 4 of them are Malonic. This one, and then these 2 sextic graphs are also Malonic. So the number of Malonic graphs goes much slower than even the total number of planar graphs. It's a subset and certainly does not exhibit the factorial growth of the total number of graphs. This is why you can solve such theories using summation techniques like Dyson-Schwinger equation techniques. Okay, so now, so this is just a general introduction where I didn't keep track of the dynamics and just looked at combinatorics of graphs. But now a lot of you have been hearing about this Sachdev-Kitaev model. And this was introduced by this particular version with Majorana fermions was introduced by Kitaev around 5 years ago. And people got extremely interested in it. It's a model where you have a large number of Majorana degrees of freedom. We will call them n sub syk. This is not the same as n in my previous slide, as you'll see in a second. And then you have interactions of q of them at a time with some randomly picked coefficients j, which are picked from a Gaussian distribution from a particular width. And this is an example of a model which actually, even though it wasn't originally advertised as such, turns out to be Malonic. It's actually an example of a Malonic theory. So if you just look by power counting in quantum mechanics, each psi has dimension 0, so this is a relevant operator for any q, and it makes the model float to strong coupling. And there it becomes nearly conformal. So there are various reviews on this by Sharashi, for example, Rosenhaus, Maldacena Stanford paper contains excellent description of these types of models. So if you look at, for example, the q equal 4 case, it turns out that, and develop, say, corrections to the propagator, you again see that only Malonic Feynman graphs contribute. So in this case, these dashed lines correspond to Gaussian average over a pair of j's. So all the non-Malonic graphs actually turn out to be suppressed in this case. And the exact solution is of interest both for studies of quantum dynamics, quantum chaos, and also for basically giving us some intuition about black holes, in particular two-dimensional black holes. Okay, so let's just focus on the spectrum of this theory. Of course, the spectrum depends on J, but in some sense, if n is large enough, whatever set of J's you pick, you see pretty similar spectra. And the reason this model is so interesting is that the spectrum is rather dense, especially near the ground state. So usually in the middle of the spectrum, because there are 2 to the NSYK over 2 states in total, there are NSYK over 2 qubits. So in this particular case, it's drawn with 16 qubits, so it's 2 to the 16 states total. So near the middle of the spectrum, you always have these 2 to the minus gaps of order 2 to the minus NSYK over 2. But in this model, these exponentially small gaps actually persist down to the ground state. And if you, this is actually spectrum for a single realization of J's, but people often also do averaging over many samples of J's, which improves the accuracy. And it turns out that the gaps near the ground state are still exponentially small in n. They're slightly less dense, but they're still exponentially small. And if you look at this, how the density of states turns on near the ground state, you see the square root type structure. And this has been studied a lot. So the square root structure is generic for random matrix models. For example, if you go back to the very first Hermitian Gaussian matrix model, which was introduced by Eugene Wigner to study spectrum of large nuclei. That, of course, has this famous semicircle law, which exhibits, so here the ground state is at E equal -2. And you see that, again, the density of states turns on as a square root. If you change the potential, it still remains the case. And for this SYK model, you actually find, if you zoom in near the ground state, you find the universal low energy expression, which is of the form hyperbolic sine of the square root. So this E is just E. The energy has been shifted so that the ground state is at 0. So it very near 0, it exhibits square root, but then it sort of grows exponentially in the square root E. And this has, of course, been a famous result lately. In the Saad-Schenker-Stanford paper, it was pointed out that this corresponds to a certain double scaling limit of matrix models where you can obtain this hyperbolic sine behavior, at least in some regions. So basically here in this low energy region, you see the hyperbolic sine, but then it levels off, and near the center, you see something approximately Gaussian for the density of states. Okay, so now, so this is of course a random model, and there are also non-random tensor models which are also Malonic. This was pointed out first by Witten, and he wrote down a very nice model. And then Tarnopolsky and I somewhat simplified it. Witten's model had ON to the six separate ON symmetries. We just took essentially the model of a single rank 3 tensor with ON cube symmetry, and then coupled these tensors according to this type of coupling whose index structure I already showed. Then this model, of course, so this is now a fermionic quantum mechanical model, and it appears to be perhaps the simplest rank 3 tensor model that you can write down. In case you're wondering, what if you just make it, say, a symmetric tensor or anti-symmetric tensor with a single ON group, then it's not hard to see that this Hamiltonian will simply vanish. So there is no option to write a Majorana model of this type with a single Majorana tensor. So now this model has, of course, 3 SON symmetry charges, which are these different commutators that you can see here. And there is one nice feature of this model is that this quartic interaction is basically the unique interaction which is dynamical, because you can write additional interactions which are squares of these charges, but these are of course just determined by group representation because they're just Casimirs of the group. So there is nothing else you can write down that's quartic. Now this is just to show why we call this vertex tetrahedral, because if you look at the tetrahedral from the side, you see that topologically it just looks like the vertex that we're adopting. Now, as I mentioned, this tetrahedral term is the unique dynamical quartic interaction in this model. There are other possible terms, which are just Casimirs of each of the groups. But if you, for example, look at the spectrum of singlet states of ON cube invariant states, then these terms simply vanish. So in the mod, but even if you don't gauge this SON cube symmetry, then these operators don't produce any splittings within each representation of SON cross SON cross SON. So it's a relatively simple looking model, but it does turn out to be very hard to solve at finite n. I will not exhibit the Schwinger-Dyson solution for which works at infinite n. I think everyone has already seen this solution many times. But let me just focus on comparison of this non-random model with the random SYK model. you can write this non-random model with these, again, in the form like SYK. But now these J's, instead of randomly distributed, just take values G times 0 plus or minus 1. And most of them are 0 because you can write them in terms of these delta functions. So this ON cubed symmetry dictates this very simple structure of J. And the number of distinct non-zero terms in this case grows only as n to the 6, while the total number of possible terms grows like NSYK to the 4 or n to the 12. So for large n, basically almost the fraction of non-vanishing terms that we can have actually is 0. So it's a very sparse model, which you would think helps us to solve it. Some better than the general SYK model. And this does happen to be the case, but it's still very hard to solve because if you throw it on the computer, the number of qubits grows like n cube over 2. So for example, even for n equals 4, you get 32 qubits, which is already a huge number. Seems like a pretty insurmountable task, but I'll actually show you some exact results for that case. But first, let us just look at so the spectrum of this non-random tensor model is very, very different from SYK model. If you go to the SYK spectrum, actually none of these states is really degenerate. The states are dense, but none of them is going to be degenerate. But for this tensor model, of course, there are different ON representations which produce large degeneracies. So to eliminate these degeneracies, you may want to focus, for example, on these singlet states. And this is a standard procedure for gauge that's why we call sometimes ADS CFT, we call it gauge gravity duality, because we usually gauge the model on the side of the field theory. The SYK model you cannot really gauge, at least not for finite n. But this model you can gauge, and you can actually count how many states survive in this gauged model, how many energy levels survive. So this was done in this paper where we carried out, basically, you just looked at the free theory, integrated out psi, and then carried out the integral over the A's. You find a pretty miraculous formula. I mean, what you would expect is that the number of singlet states grows like e to the n cube over 2 log 2 minus something of order n squared due to gauging. So, but for small n, there is a cancellation here, a pretty sizable cancellation. So for n equal 2, there are only 2 singlet states. For n equal 4, there are 36. And for n equals 6, already this sort of term is much smaller, so it goes to about 600 million. So this will be obviously very hard to solve on a regular computer, but we did manage to solve this case. This was in this paper by Kirill Petrovsky, Fedor Popov, and Bishop and Naporsky. And so first we noted that there are some discrete symmetries that act within this SON cube invariant spectrum. And then you have to do some work to figure out what precisely is the discrete group. So one interesting thing is, for example, there is a Z3 symmetry which cyclically permutes the 3 ON groups in this case, which is this symmetry. Then every interchange of 2 indices actually flips the sign of Hamiltonian. So at the end, it turns out that the non-zero energy states transform under the discrete group A4 times 2. And then so the way you try to solve on a computer for, say, n equal 4, where there are already billions of states in total, but you're trying to fish out only 36 singlet states. What you do is you add the 3 Casimir operators with large coefficients, which push up all the non-singlet states. And then you are left with a Lanz system which is amenable to Lanz's approach, because you're only interested in a few low-lying states. And Kirill Pokrovsky, who is an expert on this technique, managed to determine these states, these energies, to such high precision that we were then able to see the exact nested square root formula for these energies. These nested square roots are sort of an accident of this low n, because there are very few states mixing with each other. So you get these analytic expressions. Okay, so now let's plot these states. You see that this forest doesn't look very dense at all, right? I mean, the hope here is that you can prove that the distribution of states near the ground state will look similar to that in the SYK model. But even when you start with these billions with 32 qubits and billions of states, at the end, the number of useful states is still quite small. Then for n equals 6, you expect that the number of useful states will jump to hundreds of millions. But so the approach to large n limit is not very smooth. And it would be nice to prove that this is what happens sort of without using these diagrammatic Malonic arguments. I think we have faith it's going to be the case, but it's hard to see in practice that what's going on. And in particular, the edge behavior of this distribution of states cannot be certainly read off from this. So let's think about what other variants of such models one can look at. Well, you can, since there is no symmetry between A, B, and C, you can generalize to the case of unequal ranks. For example, if the first index runs from 1 to n1, the second from 1 to n2, and the third from 1 to n3, that's perfectly fine. You can still take the same tetrahedral Hamiltonian, just the shift constant is a little bit different. Then the Hilbert space will have dimension 2 to the n1 and 2 n3 over 2. And there are some interesting cases. For example, you can set n3 equal to 1, then you get a kind of real matrix model. If you set n3 equal to 2, you get a complex matrix model, because then you still make these large while keeping this equal to 2. There are interesting energy bounds that we derived in this paper, which actually show you, like, even if you don't know the diagrams, you can basically see that these, everything scales correctly. And then the Malonic limit, where g n to the 3 halves is kept fixed, the ground state energy correctly scales as n cubed. The gap to the lowest non-singlet state turns out to be 1 over n, and you can generalize this bound for unequal ranks. So now everything really simplifies. So this tensor model for general ranks certainly doesn't look integrable. It's a very complicated model. If someone knows how to solve it, that would be great. Now, but if you make, say, n3 equal to 2, then the bound really simplifies and actually becomes saturated by the ground state. And the model actually becomes exactly solvable. So it's a particular fermionic matrix model. Here is the traceless Hamiltonian, which we wrote down. And there is an exact formula for the ground state energy in terms of some SUN symmetry, which is a kind of spectrum generating symmetry. So you just have to do some group theory first, breaking up the spectrum into different SUN representations. And then there is, this term further breaks them to SON plus SON1 plus SON2. Just by solving it on a computer, you see that the energy levels are all integers and some units. So for example, you can work out these tables for the spectra, which we did in our first paper. But now, so more recently, so another thing we did in this paper is we looked at how much the growth of ON cross ON invariant states is. And it's much slower. For example, even for O10 cross O10 cross O2 model, where there are 2 to the 100, there are 100 qubits here. There are only 24 singlet states, so it does not make too much sense to only look at these singlet states. But they actually play some more physical role in what we're doing now, which I won't have time to talk about. But let's just look at the spectrum in a bit more detail, which is what we did in this paper we posted in February. For example, for 10, one can use this exact formula for the energies to work out log of the density of states. And you basically find no surprises here. It's extremely close to Gaussian, very smooth, peaked at 0 energy. Near the edges, it gets kind of much more bumpy, but most of the spectrum is extremely smooth and nearly Gaussian. Okay, so now let's make one more step, which is to go to fermionic vector models. Then you, for example, instead of making 2 ranks large, you make just 1 rank large. So you can have ON cross O2 cross O2 symmetry. Then these models make sense in the vectorial large limit where Gn is fixed. And in fact, this model is a slightly broken version of a related model where there is just ON cross SO4 symmetry. This model can be written down in this very nice way. There's basically each psi has an ON index and an SO4 index. And the SO4 indices are fully antisymmetrized with the epsilon ijkl tensor and pairwise contracted with these ON by the delta function of ON. Now this model is exactly solvable. This was highlighted in our recent paper. The spectrum of energies is just, if you think of SO4 as SU2 cross SU2, it's the SU2 Casimir of the first SU2 minus the Casimir of the second SU2. And the degeneracies of these states also are completely explicitly known. But now the question is, can you get mileage out of this model in the large N limit? And here we did find this certain surprise, at least something we wouldn't have expected. So when we take the large N limit, we want to make these Qs or this SU2 spins to be of order root n to keep the energy of order 1, right? Because Gn is kept fixed. Then using the Stirling approximation, we get this very simple formula, which then can be integrated to give us the density of states, the scale density of states. And this density of states is really, then this integral can be done. It's just a modified Bessel function with a prefactor. Okay, so now if you plot the log of the, so this shows actually something interesting, that this exhibits a cusp at 0 energy. The log of the density of states is just epsilon minus epsilon absolute value of E divided by lambda. And this is a comparison of this large N formula with the actual direct computation generating all states for n equal to 300. So this blue curve is the exact result for n equals 300, which is not something you could do directly, right? You need this exact formula for the energies to generate. So you get this type of density of states, and it does exhibit a cusp at 0 energy. But perhaps even more interestingly, it actually looks linear in the span of energies of order n. You see that the total span of energies is E over lambda is always of order n. Like if you did this for n equal to 2, this is plotted for n equal 300. If you did it for n equal 500, it would go between minus 500 and plus 500. This formula extracted from here, shown in dashed line, indeed is a good approximation near the center. And it shows a kind of Hagedorn transition because this density of states really grows exponentially in this region, but then gets cut off and starts decreasing. And now if you look at, for example, the specific heat, this does also, so the Hagedorn temperature is just lambda, which is this Gn, the coupling constant. And you see that this quantity exhibits a peak. So if you, these are plots for actual finite n systems, and you see that indeed the peak is honest. It's not just a figment of the large n approximation. So this very simple model actually seems to have this Hagedorn transition built into it. You can think of this model, if you go back to what this is, you can think of it as this index A can be thought of as some kind of one-dimensional index. So you have a non-local 1D spin chain with 4 Majorana fermions per site. Because it's non-local and one-dimensional, you can have a phase transition. Basically, as n becomes infinite, this one dimension actually becomes infinite because A is a one-dimensional lattice index. And you see the phase transition in the infinite volume limit. So now we're working trying to, so this is just a curiosity at this point, but we're hoping to find some physical applications for this. So now I'm basically done. Let me just quickly summarize. So this ON cube fermionic tensor quantum mechanics, which I exhibited, seems to be the closest non-random counterpart of the basic Majorana SYK model. Finding the finite n energy spectrum for it is rather complicated, and proving the approach to the large n limit. Then we dropped back to matrix and vector Majorana models, which are actually are exactly solvable for finite n, exhibit interesting spectra. For the matrix model, the spectra looked very smooth and looked Gaussian, but for this large n fermionic vector model, it exhibits an interesting cusp right in the middle. And that actually exhibits a Hagedorn transition. So it would be nice to figure out what's the dual of this simple model. Okay, thank you very much.
Thank you very much, Igor, for your nice talk. Any questions, please?
I have a short question about the vector model. So can you say, can you tell whether it is chaotic in any sense or not?
It does not seem to be chaotic. Just this particular model is not chaotic.
Okay.
Yeah, this is what you would expect because the energy eigenvalue is just for this unperturbed model. Are just very simple. They're just, so there are huge degeneracies and they're just given by two integers, which are just given by these SO4 quantum numbers. So the energies don't even depend on this ON quantum numbers directly. The degeneracies, of course, depend on N. But then when you, so it's certainly not a chaotic model, but then when you plot the log of the density of states, you basically see this peculiar phenomenon. And we think it might be generic to fermionic vector models. We have some arguments for that.
Okay. More questions, please?
I have a question. Hi, Igor. Thank you. Very nice talk. Maybe I missed it, but are these models solvable in higher dimensions?
No.
Well, which ones? The tensor model?
The tensor models, let's say, to start with, and then the other fermionic ones.
Yeah, I think the tensor model, we looked quite a bit at instead of fermionic, we looked at scalar models, say for a scalar field phi ABC with ON cross ON cross ON symmetry. Those models tend to have issues with them related to boundedness of potential and other stability issues. So they are in principle solvable, but the solution is not always giving us nice results. I mean, this, just going back to the Malonic truncation, that works in any dimension. So for example, this type of construction, we generalized it to 5-4 theory, literally with this interaction. And then you have to have renormalizability. We have to add additional ON to symmetric interaction. Yeah, the fermionic vector models, yeah, of course, those have been studied a lot, right? Like the gross Neveu model and stuff long before
Okay.
physics.
More questions, please?
Models are solvable, but of course, you know, the psi-4 interaction, it's marginal in 2 dimensions, so the gross Neveu model is asymptotically free. But so I think the specific phenomenon I'm talking about is for this quantum mechanical model, but in principle, the models are solvable, of course.
Okay, thank you very much.
Okay, maybe I will ask questions. I would like to know if there are any applications in condensed matter of your fermionic models, tensor model. If there are some models, you can describe.
So one thing, it's a little bit like what I mentioned. If you if you think of these indices as lattice sites, then
that's okay.
Yeah, then you get some kind of non-local coupling. So this, for example, you just think of some degrees of freedom on N1 cross N1 times N2 times N3 dimensional cubic lattice, and this would be this type of model. And people did look at them. For example, Chen-Ke Xu from Santa Barbara and his collaborators looked at this interpretation of these tensor models. They do work out to be rather non-local, but basically this ON symmetries require interactions to be non-local. But now we're actually looking along the lines of these interpretations, sort of adding some interactions that break ON symmetry, in particular in the matrix and vector cases, and trying to see what happens with the spectra in those cases. So potentially there could be interesting applications to quantum dynamics, especially if you start breaking the ON symmetries a bit.
Mm-hmm. Okay, thank you.
Can I ask? You just mentioned that the Hagedorn transition can be generic for fermionic models. Is it possible to guess which properties of models are essential? And concerning the previous question, is it possible also to expect something like Hagedorn transition in condensed matter?
Yeah, so the argument that we had to do with the type of diagrams that one includes. Basically, I think for these vector fermion models, if you go back to the cactus, so these cactus graphs, because they involve contraction of two fermions at the same point. So if you have just one species of fermions, then this contraction will vanish, basically. So I think the argument we had in the paper has to do with that for one set of fermions, this will vanish. So in some sense, the graph, so these are the graphs that are dominant for the bosonic ON models. But for fermionic ON models, they turn out to be not the dominant, just because in quantum mechanics, psi contraction will just give you 0. That was essentially the argument. So then one had to go to subleading order necklace graphs. And that's why we thought this could explain this peculiar feature of the spectrum. I mean, this is actually one surprise I learned from this activity. I mean, you could just say, this is just some project working with some model. Why are you doing this? But then actually I assigned it to an undergraduate student, and when he threw it on the computer, already quickly he could see this cusp in the middle. And then it took us a couple years to write it up, but this cusp does have to do with this Hagedorn behavior. So.
Okay, more questions?
Yeah, this is sort of the one. If you learn something interesting, new from this talk, I think I would want it to be this.
Okay, thanks.
Okay, if there is no more questions, let's thank the speaker again for very nice talk.